It is yeah. So we talk about homogeneous transformation matrix. Homogeneous transformation matrix is a matrix with 4 by 4 elements, and it has 3 by 3 rotation, and it has a position vector, and also it has a scaling, as we said, this to scale, and it has a perspective matrix, just which generates some perspectives, but this is really not that much a big deal for us. It's only, as I said, it is only for image processing something. Yeah, but n is here 0, 0, 0, and s is only 1. That's enough for us. The other is in robotics, you know, we have a Cartesian space as well as we have a joint variable space. You know, we have a joint variable space, or which we call it operational space. You know, we have a joint variable space and a Cartesian space. This joint variable means you have theta, for example, here A1, A2, A3, A4, A5, A6. This is the axis of rotation. So as some of you have asked yesterday, we know the orientation of rotation based on the arrow. For example, on this arrow, it is telling us there is a rotation about the given axis. Okay, the other very important point actually I would like to mention is whenever we assign the reference frames to our robot, we have to note the following as 3 pointers. One, always, you know, it is based on the Dynamit-Hartenberg convention. Always, z-axis is along the axis of rotation. Okay, z-axis, we assign the z-axis along the axis of rotation. We assign x along the link axis, or along the link, and the y-axis we follow the right hand rule. So the third axis will be fulfilled by following the right hand rule. So always be sure whenever you assign your axis, assign x-axis along the link, z-axis along the axis of rotation, and y-axis following the right hand rule. So this is really very important. Otherwise, just you will have some problems. So that, what does that mean? For example, here on figure 7.2, there is rotation along Z6, for example, for this flange, robot flange. Just here along this, there is Z-axis, so it's rotating about Z-axis. Now, if you see here, just the robot, this flange is rotating about Z5, you know, as you see it here, and this Z5 is the axis of rotation. The same is true for Z4. We are considering it only along the axis of rotation. So always we assign Z-axis along axis of rotation, X-axis along the axis of link lengths. Okay, so this we have to be sure, or just in order to avoid confusions. For example, also from this you can see now here now the base frame of this robot is assigned along the z-axis. You know, you see it here, it's along z-axis. Now, even if you consider, for example, consider only one here, just to consider this one, and maybe we remove the others and remove something like this. Now, if you see this guy, if you see this guy, for example, could be Yeah, now you see this axis, you see it, this axis is the axis is along the axis of rotation. Now again, maybe if we look at the other guy, maybe we have here, maybe here we have something here. So maybe this is joint 2. So this joint 2 is globally, it is rotating along the x-axis on global, but locally it is rotating along z-axis. But the global doesn't matter because I could change the orientation of the robot anytime, because you could change, you could relocate the robot, for example. You could relocate, maybe I could rotate the robot on z axis, and this time it is different from the origin, So yeah, so it doesn't help us, just to have to relate to this global axis. But yeah, now we have a lot, but the rotation about z axis is along this. Now, if we consider the joint to rotation, maybe which is here. This one, maybe this one. Actually, I don't know how to see that. Yeah, but actually we know these guys when we define, for example, here, yeah, just here I have one basic example. For example, here the tool center point, which is defined here, has z-axis outward, which is which represents the axis of rotation. Okay, so just this flange is rotating about this axis, so it is showing us the axis of rotation. So this one, so it is rotating along the z-axis. That's why actually we have to assign z-axis along the axis of rotation. Again, here is also the axis of rotation, but I don't able to visualize it.
I just want
to ask, so that is what we should note.
Hello?
Do you have any question?
Yes, I have a question, please. Do you hear me?
Those who you raised their hand, just do you have any question?
Yes,
yes, sir. So how is the x-axis located?
Yeah.
Hello, do you hear me?
Yeah.
Yeah. I just want to ask something, please. What about the axis? Can we change the axis positions as we want, or for instance, can we put the x rotation for degree of freedom as we want, and we can calculate it like this, or it should be z axis? It must be rotated around z axis.
Yeah, that's a convention. In otherwise, if everyone uses whatever he or she likes, then it is a problem. So in order to have a convention, this is a standard. Throughout there's a DH, which we call Dynamic-Hartenberg convention, which says it's recommended. It's recommended. It's actually maybe it's a convention or it's a standard. So assign z-axis along the axis of rotation. It is in it is in local coordinate. It is not on the global coordinate. Now this as you see, this is global coordinate. You know, this is the one you see it now. Here is a global coordinate, but this is a local coordinate. So we are talking about a local coordinate, right? So always we assign z-axis along axis of rotation. Axis of rotation means it is the axis in which it is rotating. For example, just like here, this is axis of rotation, is about z-axis. Axis of link means the link along the link links. You know, we assign x component. For example, here I assign for example, just let me consider this. Now for links, maybe I will now, for example, for joint 2, x-axis could be assigned along x-axis could be assigned along this. Along this is x. So now we assign x-axis along this, y-axis, this is x, and z-axis is perpendicular to this, is z-axis, okay, which we call it maybe like this. Now the same is true here. It is axis of rotation. We assign z here. We assign x along the link. Then we assign the y-axis along this, maybe. The same is true. For this, we assign z-axis along the axis of rotation. Then we assign x-axis along the link axis. And the third one is depending on the right-hand rule, I believe. Just use your fingers, you know, point your fingers, and then you will have something like this. And so on, you know, this way, just you could assign graphics. So always just note x should have to be assigned here, y should be assigned here, z should be assigned here according to the axis of rotation and the axis of links and the right hand rule. So this is a convention, so we have to follow it. We have to follow it, otherwise it's wrong. Otherwise it doesn't work, you know, just later. Yeah, just regarding the positioning, yeah, actually it has to be at the center of the joint, just in order to avoid any complications from the mathematics. So just it has to be at the center. If you have to put it here, it should be at the center of the motor, here at the center of the motor, and here also it is at the center of the motor. Here is also at the center of the motor. That's actually how we assign. Yeah, it's clear now?
Yes, sir.
Yeah, welcome. Good. Then let us go to the next point. Yeah, so as we said, we have 4 parameters in David-Hartenberg. These 4 parameters are assigned z-axis along the axis of joint rotation, x-axis parallel to the common normal, which is along the axis of the length. The other is complete the y-axis following the right-hand rule. This is always. Then we said we have a transformation matrix. This homogeneous transformation matrix could be represented by the David-Hartenberg convention. In the David-Hartenberg convention, we said we have joint variable, we have joint offset, and we have link offset and link lengths A and a link offset D. And we said we have two types of Dynavit-Hartenberg, and the only difference is the order of matrix manipulation. Is in the case of the older one, we have rotate Z or joint angle times translate D and translate D rotate X. So this means just just in general, you could think like rotation about Z means here the rotation about Z here means you have cos theta minus sine theta, you have sine theta, then you have cos theta, then you have 0, 0, 1, 0, 0. Then multiply dz means translate about z axis, which is 0, 0, 1. Multiply with translate about actually no, just this is sorry, that's my mistake. Translation not only this one, just we have to make 3 by 3. 0, no, 1, 0, sorry, 1. Oh my goodness. 1, then here you have 0, 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 here you have 0. This is translation matrix, which is along Z, but yeah, still actually I could use a vector, no problem. Yeah, it is. It is a translation actually, yeah, maybe no. Translation about Z axis, so it is 1, 0, 0, 0, 1, 0. It is we will translate 0, 0, dz, which is di here, yeah. Then you have to multiply with again the translation about x, which is ai 0, 0, 0, 1. This is about y-axis, yeah. Then 0, 0, 1. And then finally you multiply with the third one, which is rotation about x, which is 1, 0, 0, 0, 0. Here you have something about rotation, which is c theta minus s theta, s theta, c theta, something like this. When you multiply all these guys, you will get the transformation matrix from I minus 1 to I. Yeah, actually, this is actually what you have to do to get the matrix which is given at the letter. So rotation about Z is only rotate about Z axis. So we have a rotation about Z axis. We have translation about Z axis. We have translation about X axis. We have translation about X axis. Yeah, that's actually how we write it.
Doctor, I have a question here, please.
Yeah.
So the transformation matrix change from which, so like I go from I minus 1 to I, if there, like I can like it change, or it is the same for any reference frames? Like if I change the frame, it will change or it's the same?
Now this gives you some value, you know. Now when you consider the other approach, actually, just which is the second one, you know, the second one, which is given here, this time it changes the value because the value is not the same, you know. Here you have different values. This is completely different value, but finally the summation of all the homogeneous transformation matrix will give you the same value. Not, you know, individually it is not the same, but finally it will give you the same value. Did you get my point?
Yeah,
yeah, just this means maybe we go to here. Now you will have coordinate systems, you know, for each joint. So here you have this is different, this is different values, this is different values, and this is different values, this is different values, and this is different values. Now when you have the overall homogeneous transformation matrix, then you manipulate the whole robot just with forward kinematics, which is a multiplication of 1 times 2 times, yeah, 1 times 2 times 3 times 4 times 5 times 6. So it is 6 joints. So for each these 6 joints, you will have different values of the I minus from the homogeneous transformation of from I minus 1 to I, which difference, you know, which has a different values because this value is not the same as this. For example, here is sine theta, but it is here sine theta times cos alpha, which is not the same. Here 0, but here it is not 0. It is sine theta times sine alpha with previous offset. The current joint angles, the sine of current joint angle times the previous alpha. So it is different, but what I could assure you is finally this is the same. Okay, finally the overall is the same, that I'm sure, but the individual is maybe different. And here actually it's up to you just to decide. Actually, just you will not be penalized if you use this one approach or this approach. Just you are free, so you will not be penalized. You are also not wrong, just you have full answer actually if you do it in this way or the other way. This way, just you are free. Yeah, actually the other point actually is also very important. This is the order of multiplication. Every time you have to start from the lowest times the next, then next, the next, then the final one. This works like, for example, this is from 0 to 1 times from 1 to 2 times from 2 to 3 times from I minus 1 to I. Now this one cancels this cancels each other. For example, when you do the manipulation, the matrix manipulation, you will get this one will cancel this one, this 2 cancels this 2, this 3 cancels this 3, I minus 1 here cancels this one, and finally it becomes T from 0 to I. You know, that's why we have the final manipulation.
Like, Doctor, we start from the reference frame to frame number 1 and frame number 1 to frame number 2 and like that, yeah? Yeah. Okay.
They are a continuous multiplication with number of joints. For example, if you have 6 degree of freedom, I will be 6. So T 0 to 6 means T of 0 to 1 times T of 1 to 2 times T of 2 to 3 times T of 3 to 4, no, 2 to 3, sorry. No, 2 to 3, 3 to 4, sorry. Times T 4 to 5, then finally it is T 5 to 6. So when you multiply these matrices, the indexes will kill each other just like this. Then finally you will have the matrix which connects the first joint with the last joint. So this means, you know, in this case, you have the base frame, which is maybe which is the red point. Where was that? Maybe we make it like this. Yeah, now just you have this base frame, this guy. So this guy is connected to the last point, which is this guy. Connecting this point with this point, Connecting this point with it is connecting this point with this point. So from this to this, it is open kinematic chain. This kinematics. So this is the open kinematics chain. It is connecting. This is 0. Then no, actually 0 is, of course, this is 0. This is 1. Here we have 2. Here we have the third joint. Here we have the fourth joint. Here we have the fifth joint. Here we have the sixth joint. So we have 6 joints.
Doctor, I have another question. Sorry for many questions, but in the exam, if we have like 6 matrices, so we should multiply the 6 matrices with each other, or we should write it the 6 matrices only and don't do the multiplication?
Yeah, actually, that is actually this is a very important question, of course, on exam. Multiplying 6 matrix itself is just it is 1 hour, right?
Yeah.
Actually, I will not ask you to multiply more than 3 matrix.
Okay.
If it should go more than 3 matrix, I don't ask you. But even I will not ask you to multiply 3 matrix, but I will ask you to write each
matrix.
Yeah.
Okay.
That is the simplest way, because it is not a measure just by multiplying a matrix. I will not measure your understanding. Just I want to know whether you understand the concept, you know. That is the point. So we focus more on
the concept.
on those. So I will, but just you have to know this. The other is actually, which we call it inverse kinematics. Inverse kinematics is nothing, it is making inverse, you know. We have to make the inverse. So assume you have a transformation matrix which goes from 0 to I. Actually, I would like to mark here the order of these indices, you know. It doesn't matter. I mean, if it is consistent throughout, you see. For example, sometimes I could put the starting point at the top. Sometimes I could put here and then again some place here, you know. So if you find something like that, that's also possible. Have a notation of a matrix like this, for example, from 0 to 1 or from 0 to 1. It's possible. Okay. So in inverse transformation matrix means if you have forward kinematics, which goes from 0 to 2, means which is from 0 to 1, and maybe I will make consistent, times from 1 to 2. This time I have to make, if I'm required to do to compute the transformation matrix, which goes from 1 to 2, this 1 to 2 should be obtained by inverting this one. Okay, so this means T2 of the first can be calculated by inverting T10, by inversing this one and then multiplying with T02. This is so inverted. Now, for such inverse kinematics, we have to know how to do the inverse of the matrix. In the other way, the matrix should have to be invertible. Actually, that's why we went to make the matrix a full rank. Last time we add the last row with 0, 0, 0, 1 in order to make the matrix full rank. Okay, so that we could able to invert. So we could easily calculate the inverse kinematics. Actually, from the geometric point of view, this is also something that we could observe here. What does this inverse kinematics mean? Whenever you manipulate this robot by using a jog function here, what you are doing is you are doing a forward kinematics. When I'm controlling with a joint space, this is called a joint space. If you control the robot with the joint space with your joint variables, then it is a forward kinematics. Forward kinematics directly applies the series multiplication of, this is a forward kinematics. Okay, it is a multiplication of one joint times the second joint times the third joint times the fourth joint times the sixth joint. So that's how you are doing the forward kinematics. When it comes to the inverse kinematics, you don't have to control the joint variables, but you have to control your operational space, your Cartesian space. By defining your working or operational space along the Cartesian space, Cartesian coordinates, then you want to control the robot joint positions. So this means here, just again note, this is forward. Okay, this is forward kinematics. Now I will go to the manipulator. Maybe I will select the robot and go to the manipulator, and here, for example, maybe I will close this one. Now, if you see, I could only translate along x-axis. No, this is not. So this is yeah, just we see it here. Now I could control the robot motion only through this. Only through the TCP. Now, this is actually why we said last time we will have some problem with the singularity, Look it. Now, just when you try to manipulate with this, sometimes the robot couldn't able to solve. Sometimes, for example, here, sometimes it couldn't get the motion, and then it will change. It is just rapidly changes from some value to some greater value. For example, here, look here. I don't know if you are understanding. Look, at one instant it is moving with some degree, you know, which is unimaginable. This cannot be achieved, you know. Just how does a motor move this all position just in microsecond, which is not possible. So this is where there's singularity. Look now, look. You see, it's highly confusing, the robot. Yeah, actually, I said last time this could be avoided by defining constraints, or, you know, by limiting the joints. But this is manipulated by the inverse kinematics. So here it is doing some mathematics, which is called inverse kinematics. In the case of inverse kinematics, the robot is, for example, is calculating the inverse of θ1 from this, the inverse of, yeah. Actually, just you generate a set of equations. For example, if you have 6 joint variables, you generate 6 equations like this, and then you make simultaneous solution, and then you get the joint variables for θ1, θ2, θ3, θ4, θ5, and θ6. Yeah, actually here the point is, maybe let me make it clear. In forward kinematics, which we call so direct kinematics, you know theta values. Okay, you know the values of theta. Move θ1 30 degree, θ2 45 degree, θ3 90 degree, and then you will calculate the end effector position, okay, which is px, py, pz. But inversely, if you don't know the theta values, but you know the position of the end effector, which is px, py, pz, but the robot should have to make the motion to px, py, pz by calculating its joint positions or joint variables. So this means what does forward kinematics do? For example, here I will say θ1 is 0. Then the robot is calculating the position of end effector. Now I will say this one is 0. You see, now the robot is calculating the position of the end effector. Then here I will say 0 again. The robot is recalculating where it should have to be, you know. So this time, if I know the joint variables for all, but I do not know actually where the robot TCP should be, then I could use a forward kinematics in order to calculate or compute the end effector position, okay, or the Cartesian space. But if okay, the other is if you know only the paths. For example, you want to make some pick and place operation. For the pick and place operation, you know only the point of picking and the place of positioning. Okay, so in such situations, you need inverse kinematics, which calculates the joint variable for you. So this time, maybe for example, you say I need TCP at 600. Then you say I need a TCP at minus 1000, maybe. Maybe minus 6000. Then you say I need TCP along x-axis of maybe 500 apart. Now this time, you know, the robot was automatically adjusting, you know, its joint positions when I was changing the values on the working frame here. The same is true. This is a rotation. Maybe I will say I don't need the rotation along this, which is a rotation of the tool center point. Also, I could say this is here. Okay, this is 0. Yeah, just I could say something like this. So this time I'm doing inverse kinematics. So whether you like or not, between these joint variables and between this coordinate frame, there is an inverse matrix. No, there is an inverse kinematics model, mathematics, okay, which translates the information from joint variables to the indefector position or to the Cartesian space or maybe to the operational space, and from the operational space into the joint space. There is a mathematics called inverse kinematics and forward kinematics. Forward kinematics translates information from the joint space to operational space. And the other way, which we call it inverse kinematics or reverse kinematics or indirect kinematics, takes the information from the operational space and translates into joint space. So what does that mean? When we have indirect kinematics, you know theta, but you don't know the px, pyz, or a position vector. When you have for inverse kinematics or indirect kinematics or reverse kinematics, you know the operational space information, which we call px, py, pz, and rx, ry, rz. And then you get theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. Okay, so that's why we have forward and inverse kinematics. And you have to know this. Okay, so that is one point. Yeah, that's if this is clear. Okay, if this is clear for you, then we discuss about dynamics. Is there any question now regarding the kinematics? How the kinematics model is?
No, it's a demand. It's a demand, please. We need to answer some examples. For instance, we can get an example, then we can solve it just to simulate the questions.
Yeah, I totally agree. I will upload one exercise for you for that.
Okay, thank you.
Yeah. Okay, so now the next point is dynamics. Now just we say we have, in the kinematics, and now I think you know actually what are the parameters. The parameters are, it is position, it is about orientation, about joint space, about operational space. Okay, it is about matrix manipulation, it is about the rotation matrix, it is about translation matrix, it is about homogeneous transformation matrix, it is about calculating or manipulating the matrices and so on. But still, actually, there is one thing missing, which is about the dynamics. What will be the behavior of the robot when it performs some operation? Now, just we are actually just we are playing with this lots of kinematic simulations. Just we are free to manipulate the robot as we like and so on. And just we know this. But what is the behavior? While you do this, well, how does the robot behave? What is the effect in time, space? What is the effect due to the material property, due to its mass, due to its rigid property, due to its maybe non-rigid property, so, or due to its payload or something. So what are the effects? So that's actually what we have to address. In dynamics, actually, as we able to control the position, also we could also control the behavior, where the behavior due to acceleration, due to change in position, due to change in force, and so on. So in general, actually, that from the definition, the dynamic equations provide the relationships between actuation, contact forces acting on robot mechanism, and the acceleration and the motion trajectories that result. due to the actuation in the contact forces on the robot mechanisms, the acceleration in the motion trajectories that results is the dynamics of the robot. So we have to know how the trajectory should look like, how the robot should accelerate. So we could minimize jerks, vibrations in the robot mechanism, as well as we could avoid any effects that come due to the contacting forces, or due to the actuation forces. For example, we may be required to control the force, the torque, and also just check if the robot could be controlled precisely with the desired at the desired position, and so on. This is actually what we have to care about. So actually, why do we really need this dynamics? One is due to the mechanical design. Actually, we have a rigid body. Just these rigid bodies have inertia, they have mass, and the same, and then when they are in motion, just from the Newton's laws, there are some effects, right? If the object is accelerating, then yeah, there is a possibility that one, you could lose control, at the precise position. If you cannot control the robot at the precise position, at the desired precise position, then it is a damage, right? Just it will cause some problem. The other point, actually, why we need dynamics is to control it, to control. So as I said, just you want to control, stop here, start here. So the robot should precisely stop, and also gently, and then start, so you don't have any problem with your operation. And the other point, actually, which is also important, is for simulation. Actually, we need to study dynamics because before we make it in the actual operation, we would like to know if the desired process is what we are looking for, just in order to avoid any damage or wastes, especially in production process. Because if you are deploying the robot on the real plant site or in the real location, and if you haven't proved that it is working, then you are wasting time, production time, and also you are wasting the skills and so on. Just you are adding some non-productive jobs to the production plant. So if you use a simulation in the offline environment, first check everything and then finally come to deploy your program. Then that's why it is more easier. That's why actually we went to use simulations before we go to everything, So now in such processing, just you program some operations process, then just you check it, you check which angle is very appropriate, which passes, everything, then you study the cycle time and then just download the code and then just finally deploy it. Yeah, that way it will simplify your life. Yeah, so actually for dynamics, there are two approaches. Actually, just there are two well-known approaches. The first is maybe we can see from the Lagrange method. Lagrange method is an energy method which considers potential and kinetic energy for computing the dynamics of the robot, just depending on the energy expenditure. Okay, the energy you expend during the operation, then you could model the dynamics. And the other is actually Newton-Euler approach. The Newton-Euler approach applies the concept of Newtons and Eulers, just a linear motion and a rotational motion. If you have a linear motion, you will have a linear. If you have a linear force, you have a linear motion. If you have linear, not only a linear motion, but also you have rotational motion. for example, if you have a torque, you have a rotational and a linear motion. If you have a force, you have a linear motion, something like that. And if you combine both, you will have also the mixture of linear and rotational motions. Actually, depending on that, the Newton-Euler expresses equation of dynamics. Actually, we will see that as well. So actually here, one important point is to, because we are talking about rigid bodies are bodies that are rigid, that doesn't deform when forces are applied. Okay, that means they retain their property before and after applied forces. So whenever we consider such, first we consider the robot as a rigid body, and then just you are free to study also this non-rigid robot designs. But to start with, actually, I would like to start again also by talking about the Jacobian, and also maybe by Lagrange. Actually, if we go back and see our equation for a position from one homogeneous transformation matrix, this is nothing, it is a position. And of course, it is a composition of position and orientation. But we can generally call it's a pose. It is a pose with some orientation and with some position, okay? So if you make the first derivative of this equation, you get velocities. This velocity could be a linear velocity and a rotational velocity. So the first derivative of this gives you a velocity. The time derivative, okay? The first time derivative of this function gives you velocity. And the second derivative of this transformation matrix gives you what?
Acceleration.
Acceleration, definitely. So now when you do this derivative, you have a velocity and acceleration simultaneously. Yeah. So by using this concept, you can derive the acceleration and the velocity. But when you derive this velocity and acceleration, just there comes something which we call most of the time Jacobian. This we will have a Jacobian. This Jacobian is let's see. For example, let's see a simple equation. Now assume you have a matrix which is cos theta minus sine theta, 0, sine theta, cos theta, 0, 0, 0, 1. Then let's say L1 cos theta. You remember yesterday. L1 sine theta, 0, 1. Just take the yesterday's example, okay? Now look this. Now, if you make this time derivative d t over dt, which is velocity, okay? You get cos theta is minus sine theta times theta dot. Cos theta, sine theta is c theta times theta dot. Minus sine theta is minus cos theta times theta dot. Then cos theta is minus sine theta times theta dot. Then 0 is 0. 0 is 0. This is actually 0. This is 0. This is 0. L1 cos theta, L1 sine theta times theta dot plus L1 derivative is 0, so it is 0. L1 cos theta c theta times theta dot.
So you forgot minus in the first minus L1 sine theta theta.
For this one, right? For the first one.
Yes.
Yeah, thank you. So now just something like this here. Okay, so now just here, yeah, just here we can rewrite this one as dt over dt equals to minus s theta c theta minus c theta minus s theta 0 0 0 0 0, then also minus L1 S theta L1 C theta 0 then 0 0 times theta dot. You know, we can write something like this. So this means this is a time derivative, which we call it d theta over dt. And this is a time independent variable. This is a time independent variable. And this time independent variable, actually, if we ignore this one, and only if we focus on this one, on the linear, and on this only on the position rather than orientation, this will be position. Okay, so dp, just we only consider the position, dp over dt equals to, which is velocity, equals to minus L1 S theta L1 C theta, some matrix, yeah, times theta dot. This means this is a time independent variables, which is in the joint space, and this we call it a Gaussian. No, it's a Jacobian. Sorry, this we call it a Jacobian matrix. So this means velocity equals to Jacobian matrix times theta dot. What does this mean? What does this mean? There is a velocity, a linear velocity, which is called v. This is a linear velocity. This is a rotational velocity, right? This is a rotational velocity. This is a linear velocity. This is the orientation of the rotational velocity. Actually, we don't care about that. Okay, but here there's a velocity, which the linear velocity v, which is connected with theta dot, the joint variable velocity. Okay, the rotation theta in time, which is connected, which is linked, okay, with Jacobian. So the linear velocity and the rotational velocities, or linear and non-linear velocities, are related by a Jacobian matrix. So a Jacobian is a Jacobian matrix. Actually, here is a matrix which linearly connects, which connects the linear velocity with the nonlinear velocities. You know, it is a mapping which maps. Jacobian velocity is a matrix which maps the rotational velocity with the linear velocity. Okay, so it is a Jacobian matrix. So the Jacobian matrix is a time independent. It is, you could now, if somebody asks you, define a Jacobian matrix, then you could say Jacobian matrix is a time independent variable that maps the rotational velocity with linear velocity. Okay, something like this could be okay. Now, so the Jacobian could be defined with a matrix, actually, as you could see it here. Yeah, but it is a partial differentiation. Actually, you could also calculate just manually by doing some differential equations. But actually what I would like to tell you is this Jacobian, because now we are considering linear motion as well as the rotational motion, because here we have separated, we separated. Here we are only considering the linear, it is a linear, but here there is no linear, I mean a linear means just here I'm considering only the position of the vector for this, but also there is some part which is also non-linear for this section. Okay, so for that also just we have to make some distinction. For this part also we have to make a distinction. So we could have a Jacobian which is linear, which we call maybe for only changing in the position, maybe we call it a prismatic, maybe we call the other one is it is revolute or orientation, wherever you have rotation. Now this case, actually this case only works if it is only linear, but if there is a rotation as well during, then there should be another Jacobian which is called G naught. Yeah, but in general, what is Jacobian? Jacobian is the partial differentiation. It is a partial derivative of the, for example, x component into with the each joint variables. Yeah, for example, if you have where you have I equals to 1, 2, 3, 4 or something, or just you could use this approach where you have a Jacobian matrix. This is a linear, this is a rotation, and this is actually just a very simple trick. How you calculate GP and the G naught is just directly forward. GP is Z axis of J minus 1 times PC. This is center point, okay? It is the center of the mass. For example, if you have these robots, just I would like to make it clear. Now for this robot, okay? Before we start, actually, just to define Jacobian and everything, we have to simplify the model, right? Just we have to simplify. The first way to simplify is to define the center of mass, okay? Where is the center of the mass? Maybe I could say, for this, the center of mass is maybe here, PC1. This is for joint 1, and for this I could say this is the center of mass, okay, which I say it's PC2. For this I will say here is center of mass, which I will say it's PC3. For this link, okay, for this link I will say this is center of mass, PC4. For this I will say it is here. No, this doesn't work. Actually PC4 is the same. Here I will say PC5, then I will have PC6 here for the last one. It is nothing, it is center of mass. Then this is center of mass. This is the center of coordinate system, where the reference frame. Here is 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 the reference frame. there is a difference between the PC and the reference frame. Reference frame is at the center of the joints, right? At the center of the motor. PC is the center of the link. Okay, the center of mass. It's not center of the measurement, but it's center of mass where the link is. For example, unfortunately, this has no dynamics actually. Also, if somebody asks you what is the disadvantage of process simulator, just you could easily say it doesn't perform dynamic simulation. A force simulation is not possible. If that is the case, actually, we should see by making the force, for example, at 0, just why this robot falls, but this is not the case, so we cannot do it here. They didn't implement it actually. But what I want to tell you is the center of mass is the center where the particle has a center. Okay, so now just first we take the center of mass. Then from the equation, actually, it's also good to note here, from the equation of this, from this equation, it says take z axis of the previous axis and then multiply this with the, just this is a multiplication matrix with the center of mass minus the position of the first, the previous joint reference frame. So PC, for example, let's say dp of 4, zi minus 1 means take z of I minus 1, take z of I minus 1, z of I minus 1 means if you want to take I equals to 4, it is z3 multiply with PC 4 minus reference PJ3. PC4 means this guy. This is PC4. PJ3 means this guy. The distance from this to this is PC4 minus PJ3. Z3 means the Z axis of this, which is a rotation. Okay, which is the rotation. So Z3 means take the Z axis of the rotation. Rotation means the rotation of Z means take the third column. Just take only the third column. Here, this from the third. Just for example, you have defined your matrix, then you will take the third column means for example, like this. It is, for example, Z00, Z0 is 001, Z1 is minus, sin S1 is minus C10, S1 something, this is what you take. This is the third component, just maybe to get complicated when you have many multiplications, but you take this axis. So Z3 times the distance. So it is this, the Z axis times this distance gives you a Jacobian matrix for linear, okay, for linear. For the rotation, which is really very simple, is take the Z axis of the previous joint, which is a multiplication, of course, So if you want to make the Jacobian matrix for rotation about 4, this is actually Jacobian of P4. Jacobian of O4 means Z3. Just easy. you know, just easy. Just easy. So this is a trick actually, just to get through this Jacobian. So once you know this Jacobian, the other is actually is to only to calculate the formula. Actually, I will tell you how this Jacobian matrix is going to be combined to the Lagrangian method. So in general, these equations are going to be applied in the Lagrangian equation as the following equation. This equation, which is a generalized force, which could be torque or force. Okay, we don't have to define this now. It could be a force or it could be a torque. Could be, we say it is a generalized force, is capital D. It is the derivative of time derivative of the partial derivative of Lagrangian variable with a joint acceleration velocity, joint velocity minus the partial derivative of joint Lagrangian variable over the joint variable Q. Q is joint variable, which we call theta or A actually in COCO. But Lagrange means, Lagrange is, you know, first then we have to know actually what this is. It is the difference of this is actually tau, we call it tau, it is Greek word tau. This is kinetic energy. Lagrange is the difference of kinetic energy minus potential energy, where kinetic energy means from physics it is, the kinetic energy is from physics it is 1/2 m v square plus 1/2 I omega square, right? From your physics actually, just this, no, we are not creating anything here. From this, from your physics, as a, by considering a particle, okay, as a particle, or maybe just as a rigid as well, we call U is mass times gravity times height, right? Something like this could be from physics, nothing else. Yeah, but now here we rewrite it again, you know, in a very robotic way, just in a robotic way. This from the physics, kinetic energy is 1/2 mv square plus 1/2 IW square or something. Then you say the potential energy is some kind of mass times gravity, something.
Essentially.
Maybe height is not necessary actually. Here it is mass times gravity is weight. Then potential energy is height, yeah, images. Yeah.
Essentially.
Yeah.
Sorry, 3 things is important for me today. First of all, is that your speed of teaching is so fast. We needed time to write some of these notes that you write in the right side of our lectures. We couldn't write our notes because you're teaching so fast, because I know you have less time. And the second thing is that we are a little confused about, because today we have many type of equations, but we don't know how we will ask these questions in our exams. You know, we have to memorize the equations. I don't know. Can you explain more? Because it's make worry, because we have only 1 week until the exam, 2 weeks to exam.
Yeah, actually, just the point is you don't have to be exam oriented. Just you have to focus more on for understanding. You know, just exam is the second. Just for me now, just the first thing is just to let you understand just the concept behind the magic behind a robot. You know, that is the first thing. The second is actually, yeah, exam is yeah, I think you have seen the model this last time, so just it will follow the same procedure. And yeah, I will ask you first just regarding the how you understand, how you also not only understand, then also how you explain it. That's actually what I will ask. Yeah, then regarding the speed, of course, I have to just be fast, otherwise I cannot finish it. Yeah, but regarding the equations and so on, just maybe it is, you know, when you have first exposure, it seems like that, but it is not actually. Just it's very limited. Just so far, you know, what I was discussing was I revised what we had last time with the kinematics, just in detail. So in kinematics, we know homogeneous transformation matrix. We know these homogeneous transformation matrices are composed of 4x4 matrices, which are derived based on a de Navit-Hartenberg conventions. De Navit-Hartenberg convention is nothing. It is a convention to represent your homogeneous transformation matrix in a systematic way by describing your joint variables. Joint variable means theta, which is a variable which changes, okay, in your robot mechanism, which we call it actuation angle, maybe just joint variable, okay. Then the other is a vector position, which we call it px, py, pz. We could call it also operational space, which is, we call it again also a Cartesian space. It's nothing, this a way of representation. Cartesian means x, y, z. Operation means where the robot performs the task. So we say it is where the robot performs, operates. So we say it is operational space. And we say joint space because it is a robot joint, which is in angle. Joint space is in angle, operation space is in XYZ, in Cartesian coordinate system. That's why I said we will have operational space and joint space. It's nothing. We have a homogeneous transformation matrix. This homogeneous transformation matrix have a purpose to derive the kinematic chain from the base to the end effector by calculating based on a joint space theta. If you don't have if you don't know your exact point, you know, you could use a jogging manipulator or a teach pendant on the robot and then move the robot just to this place, and then by trying the error you will get your values. Or if you know the joint angle specific, say theta 1 is this, theta 2 is this, theta 3 is this, something, and then you will get the result. The other ways, if you have a inverse kinematics model, only by letting the robot the end effector position or the Cartesian space or the operational variable, then you let the robot to automatically compute for the joint variables. But this time, there is a possibility that the robot could go to the singularity configuration. Then if this singularity configuration happens, just you have to solve it by constraining the joints and repositioning your just robot, or the if that's not possible, then the operation space, you know, where you have to do the work. This is actually where you have to do. Then the other question could be actually that I didn't mention was, how do you know that whether there is a singularity or not? That's actually there's a method called the determinant of the Jacobian matrix. Now we have discussed how to calculate the Jacobian matrix. From the Jacobian matrix, you will calculate the determinant of the matrix, and if the determinant is equal to 0, then there's a singularity for that particular configuration. In such situations, just you have to avoid singularity by avoiding the joint variable parameter that leads the robot into a singularity configuration. So that is what we discussed. Yes, I think last week I showed you some videos where there are some configuration of this singularity. Now the point is, in this situation, we don't have any. We didn't pay attention to the trajectories, the motions. Just we are only telling the robot to move joint variables here and there, but that is not the real. In the real environment, there is a dynamic effect which comes due to the mechanics, due to the kinematics, due to the mechanical component, and due to the control and so on. Just you would like to control the robot precisely at some specific position. In order to do that, there is inertia of the robot which affects the performance of the motor. So you have to know how you compensate these dynamic behaviors by including a dynamic model into your kinematics. Otherwise, only a simple jogging operation doesn't solve industrial problems. This is nothing. Just this is a kinematics. Nothing is here. It's only forward and inverse kinematics. Nothing. Just behind this software. Just this is a software that you could easily develop just in some days, maybe. I mean, just from this is nothing. You have a geometric model, CAD model, and you have only kinematics. Here you have only kinematics. It's nothing. Just this is something that you, as a layman, any layman can develop. Just not Siemens. This here in Siemens, just they didn't implement any dynamics property and so on. But of course, they have some wonderful buttons here, which we are not now taking care. But just here, the point of our today's discussion was there is nothing here. It is only a kinematics. So I would like to have a dynamics property where the robot should be controlled for it is dynamic as well. So for that, I would like to know actually the mass property, the center of mass, the center of the reference frame, and also I would like to know how the derivative of the transformation matrix behaves. That means which is the time derivative of the homogeneous transformation matrix in time, and then I see the velocity, then I see acceleration, and then if I got velocity and acceleration, then I could develop mathematics from Newton-Euler equation. Newton-Euler means it is the summation of force equals to mass times acceleration from physics, right? From simple physics, force is mass times acceleration, torque is inertia times angular acceleration. So I would like to apply this concept. To apply this concept, I need mass and where the mass is applied. And I need velocity and acceleration. I need the acceleration, I need the inertia of the robot, so and so on. So these properties I have to insert it into my equation and then finally develop my equation. It's nothing. So it is not too much content. It is only we have forward kinematics. Just bear in mind forward kinematics, inverse kinematics. Then Jacobian concept. Jacobian is a linear mapping between linear velocity and the angular velocity. Then I have now a Newton-Euler and a Lagrangian equation. This force, and then finally we will have trajectory planning, which comes the last. It is not too much information. Maybe when you have the first exposure, yeah, it seems like that. Yeah, but during the exam, actually, just I will, yeah, just ask the concept. For example, you should have to know actually how to calculate the dynamics of the robot using a Lagrangian equation. For example, you should be able to describe what is a Lagrangian. So Lagrange is, it is the difference of kinetic energy and potential energy, nothing. This difference gives you a Lagrange variable. The derivative, the partial differentiation of Lagrange variable with respect to joint velocities gives you the difference between the time derivative of the partial derivative of Lagrangian variables with q dot and partial derivative of Lagrange with normal q gives you the force or the torque that the rod joint is applied. So this means you have motors, right? Just here, process simulator doesn't know if it is a motor or not. Just here, for example, just here, this is a motor. This is a motor, but process simulator is considering only just as a simple object, okay? But it is this is a motor. This black box is a motor. So I need a motor equation to be inserted there so that I will have a real behavior of robot. But no, here it is not. If you go to the real robot, it's not possible that I could manipulate this robot with this speed. How could I move a robot like this, just in microsecond, just like this, in real environment? It's not possible. So just it's only doing some mathematics and then just showing the motion. This is really not possible in real environment. When you move a robot just on this axis, it has maximum maybe 4 meters per second. But now I'm doing everything just in just microsecond maybe. I could achieve just this is not possible in a real environment. It's not possible. You cannot make a robot move like this. This is why, because it has no clue about the behavior of the actuator, how the motor was working and so on. So we have to go beyond process simulator, we should go beyond the process simulator. Say, this is a motor. So since it is a motor, we need a motor property where we have force due to the mechanical property and the electric property, not only the mechanical system, but due to the electrical system. You as a mechatronics guys, you have to consider both things. It is mechatronics, it's a combination. Just you have the mechanical system, you have the electrical system, you have the computer system, the IT system. So just you understand what should be the behavior of the mechanics, the mechanical system. Then you have a motor. This is stepper motor. In stepper motor, you have different components. You have a rotor. You have just so many things. And then you have to consider these variables. And then you will have some electromagnetic fields. This magnetic field generate something. And then how does this affect the mechanical system? Then you go to the control, and then how does this affect my motion? How does this affect my control system? And then on top of that, you see how does this affect my software? How does it affect my program? Something like that. So just you will combine all these things. Actually, that's why it's more interdisciplinary. But the point here is why we need this dynamics is just to understand the behavior, okay? Just the behavior behind. Just this behavior, just now we discuss it with, we have discussed now, but the question is, how do we implement it? How do we implement it? Yeah, how do we implement? To implement, we need a controller which takes into account the effect of this mechanical system with a simplified model, of course, with some mathematics, also with some programming language. So for that, first we just let us focus on the mathematics. From the mathematics, there is a Lagrangian equation, Lagrangian method approach, which is a time derivative of this. And then there is a corresponding equation for Newton-Euler. So Newton-Euler says torque or force, a linear force or a rotational force is mass times acceleration plus c times q dot. It is this is actually in all the classes you see it as you learn maybe as damping coefficient, something, you know, just the damping coefficient with the velocity, and then you say then finally you could say gravity. So I remember in some lectures, just most lectures, you know, you will learn something like, see this, mq double dot plus cq dot plus gq equals to torque. This is actually just for now, let's keep it. So this is the generalized equation for Newton-Euler. Yeah, and then this is the generalized equation for Lagrangian meters. Yeah, so the question is what is behind this equation? That is what is interesting. What is behind? So what is Lagrange? Lagrange is the difference of kinetic energy and potential energy. Q dot is velocity. Q is joint variable, which is theta 1, theta 2, theta 3, theta 4, 5, 6. Mass is a mass inertia, which is mass, just simple mass and inertia. Okay, so we have to combine. Just why we have a capital M here, it is a combination of linear mass plus inertia, the inertia of the robot links. Yeah, as you have mentioned, some you mentioned now, the equation is of course not easy. Yeah, it's not easy forward. You have to do some matrix manipulation. Actually, just what makes it complicated is actually it is the matrix. Because of the matrix, you have to, one, you have a matrix of so many variables or so many variables, yeah. And the other is you have to do the different joints, for example, for a single robot like this. Yeah, what makes the robotics just a little bit difficult is you have many joint variables, right? Just here, for example, you have 6 joint variables. So just you are not talking about dynamics of a single joint, just you are talking a dynamics, a cumulative dynamics of a 6 joint variables. So this time it is a little bit yeah, difficult, but yeah, but at least you have to able to understand the high level descriptions. You know, you could be able to even if you couldn't manipulate, you know, the matrices, you know, of course you may not be expected, of course, because nowadays there are nice programming languages which can easily manipulate the matrices, you know, easily, so you don't have to worry about a matrix multiplication or something, you know. Also, I will not ask you like that, and also it's not in the scope because now there are so many softwares which in programming, you know, with MATLAB, with Python, everything, you know, you can easily manipulate these matrices. And also, yeah, what actually I would like you still to know is what is yeah, Lagrange equation, what is Newton-Euler equation, what is Jacobian, what is singularity configuration, what is forward kinematics, what is inverse kinematics, what is DH convention, yeah, something like this at the high level. And then what is dynamics itself, what is kinematics itself, how dynamics will affect the production process, it's your automation system and so on. What should you take into account when you make these things, and then how does it affect my trajectories or maybe my operation, the accuracy, maybe the quality of something, you know. This is what you should be able to discuss, at least, you know, verbally, just orally. You have to able to write to discuss these things, but also just, yeah, just also the high level equations. Just I will not ask you some details like this. I don't ask you something like this, but I will ask you something like this. Just you have to able to discuss this. What is this? What is mass? What is acceleration? What is this Coriolis effect? What is gravity? Then what is Lagrange? What is Lagrange formulation? What is Newton-Euler formulation? How do you relate Lagrange with Newton-Euler equation? Something like this is something that you should be able to demonstrate. Actually, how is it, guys? You are